In the last video, we had wrapped up the design of the arithmetic logic unit. With that, we have one of the largest components of our CPU completed. We'll of course get around to building the CPU, but in order to do that, we must explore a component that I find rather fascinating, the register. What makes the register so cool and important is its ability to hold data. We can throw numbers through the ALU all we want, but without the ability to hold on to certain numbers, we end up losing something vital. If we skipped putting registers in our CPU, it would constantly forget what numbers you just used. Imagine doing 5 plus 4. You know that your output is 9, but you do not know what numbers led you to that answer. Not only that, but some registers allow us to do specific things such as access memory or keep track of where we are in a program. So with that, what makes up a register? Let's start simple. From the previous videos, we should somewhat recognize the symbol. It is what we call the OR gate. Let's do a really quick recap on what it does. If I have two buttons and an LED as the output, we can see that when I press either of the buttons, the LED turns on. The OR gate is often used to combine two signals into one signal. Okay, so now I'm going to slightly modify this circuit. I'm going to remove one of the buttons and I'm going to add a wire connecting the output to one of the other inputs. If I press the button and let go, you'll see that the LED is staying on. As of now, the LED will just stay on. With this circuit state, there's no way to actually turn off this LED unless we remove the power. As you probably suspect, we can modify this so that way we can turn this LED off with another button. However, we need to change one thing about this logic gate that we are using. I would like to invert the signal of the OR gate. So whatever the output was before, it is now the opposite. We can actually condense this into a single name. It is called the NOT OR gate, aka the NOR gate. Or NOR. Okay, so what exactly am I getting at? If we use two of these and connect them like this, we get what we're talking about. We can turn on the LED, and this one turns it off. This actually has a name. We call this a set-reset latch, but you may often see its abbreviated form, SR-Latch. It's pretty neat, and you could just use this right away in your projects to store little values. However, using the SR-Latch for important data storage can cause issues. When your system runs on a clock, like literally every computer, sometimes you have values that take a second to settle. The SR-Latch is of course very helpful and is the foundational block of memory as we know it, but it's just not suitable for this case. So we kind of need to make something new. Luckily, we do not need to dismantle the SR-Latch. We just need to add a little bit to it. Right now, the SR-Latch is difficult to use. If we want to store data to it, we would have to clear it every single time and then store new data. What we can do instead is tell it to load whatever value is coming in on the data pin. So this means that we need to rename our set and reset pins. Set will become data, and reset will now become load. Now it's time to add our logic. Simply, all that we are adding on is just two more AND gates and a simple NOT gate. It can look confusing, but the reason that this works is because if both of the load and the data are on, then it makes the set pin turn on and the reset off. In order to turn reset back on, we simply enable store with data off. With that, we now have the D-Latch. This is an easier to use SR-Latch in my opinion. So now we are to our last building block of memory, the D flip-flop. This is what solves this settling issue. We will officially include the clock as one of our input pins. Yet again, the D flip-flop is actually fairly easy to understand logic-wise. All we need to do is make another D-Latch and add in another AND and a NOT gate. The original latch that we had will now be called the master D-Latch, and the new D-Latch is called the slave D-Latch. As you can see, we now have three buttons: data, load, and clock. What we need is for the settled data to be the output of this whole circuit. It works like this. When the clock starts to pulse, aka when the clock is high, then the data will be loaded into the master D-Latch, as long as the load pin is also enabled. Now, the data may bounce. As you can see, when I enable the data pin, you can see that the master D-Latch turns on and off, but the slave D-Latch isn't changing at all. Only on the falling edge will the slave D-Latch store whatever is in the master D-Latch. Like I have been saying, the values may bounce, and we may wait for them to settle. The D flip-flop is quite stable. It is important to note that sometimes your values may bounce during the whole cycle. This can especially be problematic on breadboards. This is why clock cycles need to be slower on these types of computers, because the wires are longer and the other things can lead to an instability that needs a few seconds to officially settle. Some of you may have noticed this board in some of my videos. It is a clock circuit that I designed for PCB and had printed from Ivan, a PCB company. I've been using it in some of my projects and it works really well. So I'm very proud to say that there's no better place to get a printed circuit board than with this video's sponsor, Ivan. I do want to show you how easy it is to order. The first thing that you need to do is export your PCB as Gerber files. Once that is done, the rest is on Ivan's site. If you haven't designed a PCB before, but you still want in on the fun, I have the Gerber files for free on my Buy Me a Coffee. The link to that is in the description below. So once you have your Gerber files, the next thing you need to do is make it to Ivan's page. You can use my creator link in the description below, and you'll be met with this page. It informs you that you are eligible for some nice welcome credits, $60 off of your very first PCB prototype. Once you click the Get Your Welcome Credits button, you'll be prompted to create your account. Personally, I like the sign in with Google feature. Next, you can scroll down here to PCB prototype and select Quote Now. You can select PCB assembly if you would like, however note that this option will not grant you the rewards from earlier. From this page, you can simply upload your Gerber files that we exported at the beginning of this segment, and it will autocomplete everything on this page. Check everything over to make sure it's all correct, and then click Add to Cart. From here, select your PCB and start the ordering process. This is just like every other site, so I will not guide you through this part, but once you put in your shipping and your billing information, you can then place your order. From this point, all you have to do is just wait. And that's it. Thank you, Ivan, for being the sponsor of this video. So now we have all of the knowledge to build our register. The register is a little storage space for one number. CPUs have many of these, but the computer that I'm building in my Build a Computer from Scratch series will only have 4 registers. Just a little side note, I actually started that series exactly a year ago from May 28th. Pretty crazy how the time flies. So now we need to build a register using our D flip-flop knowledge. All we really need to do is just build 16 of these D flip-flops to assemble our 16-bit register. If you're making an 8-bit CPU, then you'd only need 8 D flip-flops. So just make as many as you need. All you really need to do is connect all of the load pins together, and you do the same with the clock pins. We do this because the register is one whole unit. We want to load the data all at once, as the bits will be our stored number. This number can be as little as 0 and as large as 65,535, which is pretty large for a simple computer. The register was pretty easy to assemble, as you can see, but it really is the application of the register that we should really study. So let's look at one of the registers that will be in the CPU. We will start off easy with what's called the D register. The D register is what is called a general purpose register. It doesn't really have a super unique job. The register will be responsible for holding the X input value for the ALU, but the output of the ALU can also be stored into the D register, so it's pretty general purpose. The next register that we'll be having a look at is the program counter. This register is simply counting up with every clock cycle. It starts counting from 0 all the way up to a max of 65,535. The purpose of this register is to keep track of where we are in our program. We start executing the program from line 0, and we go line by line after that. You actually can load values into the program counter, and that will start reading the program at this line. If you're a programmer, this is how if statements, loops, and functions are executed. Although, we will look more into this a little bit later. Alright, so the next register that we're going to be looking at is a little bit of a hefty one. It is what is called our A register. The A register can do everything that the D register does, but it's responsible for a lot of what's going on in the CPU. So let's start listing those. The A register is what accepts A instructions. A instructions are just numbers that load from the ROM directly. So if I want to load the number 100 to the D register, I would first have to load it into the A register and then set the D register equal to the A register's output. I would first have to load it into the A register and then set the D register equal to the A register's output. I'm sorry if that sounds like a lot, but hopefully you get used to it quickly. Another thing that the A register does is determine which value we would like to load into the program counter. So if we would like to jump to line 10 in our program, we will load 10 into the A register, and then initiate a jump command. Similarly, the A register also holds which memory address we would like to access. So if I want to access RAM address 1024, I will load that directly into the A register and then read or write to RAM. The last register that we're looking at is the M register. The M is for memory access. So if I would like to read or write to a specific RAM address, I would throw it into the M register. So like I listed above, if you would like to access RAM address 1024 and then store the value 10, I would need to load 10 into the A register, set D equal to A, so that way we have our data stored for later. Then we load 1024 into the A register. Lastly, load D's value into the M register. You would of course have to get used to preparing your data before you use it, but with that, we are done with our register section. Bonus level. Sorry, I just had to do that. Although I didn't plan to include memory into this video, I figured there was no better place to include it, but here. Due to the amount of components I would need to build this in person, I'm really just going to simply have to show you the graphics rather than real builds. Please forgive me, although you may now understand why RAM is quite expensive. Luckily, to explain memory, we don't really need to stray away from registers because RAM is basically just lots of those. Well, SRAM to be specific. Modern RAM, aka the stuff that is in our phone or your gaming PC, is known as DRAM. We have the two different types because SRAM is really expensive to manufacture and not really feasible when you need gigabytes of memory. Okay, so how exactly does SRAM work? Let's start off with one register. I'm going to label this 0x000 for address 0. We know how to read and write to registers, so I really don't need to bore you with more details. Just know that we have a load bit here, which just tells us when we want to load the incoming data. It is when I add another register in here that things become more complicated. Now, I need to be able to select between RAM addresses. As of now, we only have 2 RAM addresses, so I can simply add one extra bit for selecting which RAM address we would like to access. So now we have 2 total bits, for one load and one for selecting RAM addresses. So what we're going to do is feed this load bit into a D multiplexer and connect the 2 outputs of the demux to each address, when we simply connect the selector bit of the demux to the address pin. This may look like a lot to understand, but once you understand how it works, it should feel pretty simple. Now I haven't mentioned how we read data from the newly established memory. Simply, we use a normal multiplexer. So whatever address number we used for the demux to load a value, that is what we will connect to the multiplexer. So when we enable address 1, that will either read the data at that address, or if we enable the load pin, we will just load a new value at that address. Really, from this point on, memory doesn't get any more complex. If I want to add another address, then I will simply use another mux in demux to compensate for the extra addresses. Normally, you do not use a weird or odd number of addresses, so 3 addresses just won't do. You can move up to 4, that way all of your address bits will be utilized. I will say that you probably want to use a number that is 2 to the power of X address bits that you would like. For my computer, I'm doing 15 address bits, so 2 to the power 15. Primarily because I do not want to address negative numbers, and I really do not need more than that for now. So this means that I will have 2 to the power 15 addresses, or 32,767 to be exact. So imagine hand assembling 32,767 registers to be used for in memory. In my computer, I'll be using an IC. Hopefully you can all forgive me for that. I hope that this demonstration helped. I know the last video mentioned that I would work on the CPU, but then I kind of realized that the CPU needs parts that we haven't even talked about yet. So to my knowledge, I think that we should be ready for the CPU now. That video will be quite bulky, but I'm very excited. It really is some fun stuff. If you have any questions or suggestions, please let me know in the comment section down below. Also, if you're looking for a PCB, please be sure to check out Ivan. They do produce some really quality PCBs. And I think that's it for this video. I will see you all in the next one. See ya.